Welcome to our presentation on fundamental technique in data science called Principal Component Analysis or PCA. My name is Pattarapong Chaichuen.
And me, PORNCHANOK PHUAKTAO.
We are from CSC262 and today we are going to explore how we can simplify complex data using linear algebra. Let's start with the big question. Why do we need dimensionality reduction? The motivation is simple. Modern datasets are huge. They often have hundreds or thousands of features, many of which are highly correlated. This high dimensionality makes our data difficult to visualize and dramatically slow down computation time. Our objective today is to show how PCA helps us to solve this problem by reducing data complexity, by keeping the essential information. Specifically, we will demonstrate the mathematical foundation of PCA, focusing on eigenvalues and equivalence. Visualize a high-dimensional datasets in much lower dimensions, specifically 2D and 3D. And finally, compare the accuracy of machine learning model before and after applying PCA. Our goal is to bridge the gap between linear algebra theory and real-world machine learning applications. So, what exactly is PCA? At its core, PCA is a linear algebra technique used for dimensionality reduction. Its main function is to convert a set of correlated features into a new set of uncorrelated variable called principal component or PCS. The key idea is that each principal component represents a direction in a data with the maximum possible variance. This brings us to the key concepts which are at the heart of PCA, eigenvectors. These define the new direction of principal components that capture the maximum variance in the data. Eigenvalues, these measure the magnitude of the variance in each of those eigenvector directions. Our ultimate goal is to keep only the top few components that collectively capture about 95% of the total variance. PCA is an extremely powerful technique, and it is entirely built on a solid mathematical background. In simple terms, the process revolves around three main formulas. First, we calculate the covalent matrix C, which measures the relationship or correlation between the original features. Second, we perform the eigen decomposition. This is where we found the eigenvector, which are the direction of maximum variance, and the corresponding eigenvalues, which indicate how much variance is explained by each direction. Finally, we project the original data onto a smaller set of the base eigenvector to get our transformation low-dimensional data C.
For this project, we use the ELITE dataset, which contains 150 samples for numerical features and 3 species. We perform our analysis in Python using NumPy, Matplotlib, and scikit-learn. The workflow involves in 5 main steps. First is loading and standardizing the data using standard scalar. Second is computing PCA from the covalent matrix. And next we will selecting the number of components using cumulative explained variance. And next is visualizing the transformed data in 2D and 3D. And finally, comparing model performance with and without PCA using logistic regression, KNN, and decision tree. Next, I will demonstrate the implementation part of this project. We use Python to perform PCA on the ELITE datasets, visualize the result, and compare model performance before and after dimensionality reduction. This graph shows the cumulative explained variance for each principal component. From the curve, we can see that the first two components capture about 95.8% of the total variance, This means that almost all meaningful information from the original four features can be represented in just two dimensions with minimal loss. Therefore, using two components is an efficient and justified choice. These 2D scatter plots show the eyelid dataset projected onto the first two principal components. The results are quite intuitive. Setosa show inlet form a clearly separated and compact cluster. Versicolor in green overlaps slightly with Virginica. Virginica in blue shows some overlap but still maintain a recognizable pattern. So, this demonstrates that PCA successfully visualized the overall data structure in only two dimensions. When we include the third principal component, the class separation becomes even clearer. The additional dimension capture variation that isn't visible in the 2D plot. This helps distinguish versicolor and Virginica more effectively. This highlights how 3D projection can reveal deeper structure in the data. Next, we compare model performance before and after PCA. Across logistic regression, KNN, and decision tree, the average reduction in accuracy is less than 2%, which is extremely small. At the same time, PCA improved computational efficiency and provide much clearer visualization. This shows that the trade-off between accuracy and dimensionality is highly favorable. This table summarizes the accuracy value. Without PCA, all models perform between 96 and 98%. With PCA, using only two components, accuracy remains above 94%. This confirms that PCA successfully reduced features dimension while preserving model reliability.
To conclude our presentation, let's summarize the key insight. We demonstrate the PCA efficiently reduced the IRIS dataset to two components while retaining approximately 95% of the total variance. This allows us to maintain a high level of model accuracy while substantially improving the computational efficiency. We also note some limitation. PCA is a linear technique, meaning it assumes the relationship in the data are linear. Also, the new principal components are not as easy to interpret as the original features. For future improvements, we have two main avenues we plan to explore, focusing on enhanced performance and wider applicability. First, to address the linear limitation, we will try nonlinear dimensionality reduction technique like kernel PCA or TSNE to handle dataset with nonlinear structure. The expected result is to clearer cluster separation for more complex real-world data. Second, we plan to apply PCA as a robust preprocessing step for more advanced models. We want to combine PCA with methods like clustering algorithm or neural network to archive significant reduction in model training times and higher efficiency when working with very large datasets. And lastly, our key takeaway is that PCA is a powerful tool that effectively bridges the linear algebra theory and the machine learning practice, transforming complex data into simpler, more meaningful representation. With all of that, we conclude our analysis of principal component analysis. We hope we have clearly demonstrated how this technique is indispensable for the navigating complexity of modern data. Thank you once again.